This tetrahedron will consist of 4 congruent triangles. Let's draw this out and see if we can figure out where the lengths are. Let's say we have this tetrahedron PQRS, and let's say our front face here, triangle PQR, has side lengths of length A, B, and C. If we look at this other triangle to the right here, triangle PRS, one of its side lengths has length of B, and then the triangle in the back, triangle PQS, already has a side length PQ with length A. Edge PS is on both of these triangles, PRS and PQS. And since all of these triangles are congruent, they're all going to have sides of length A, B, and C. So this edge cannot have length A or B, or else it will result in an isosceles triangle. So we must have that edge PS has length C. We can continue this and complete the rest of the lengths of the edges, and we will see that pairs of congruent edges, for example, PS and QR, will be skew. This means these edges are non-parallel and non-intersecting. By the symmetry of this tetrahedron with 4 congruent triangles, the edges can form the diagonals of a rectangular prism. So for example, we can put P, Q, and R from our tetrahedron above, and here are the edges forming the diagonals. We should notice here that this angle PQR of the tetrahedron is going to be less than the angle that forms the corner of this rectangular prism. For example, angle TQU here at the bottom. This is 90 degrees, which means all of these angles in the tetrahedron are acute, and so all of the faces are acute. So to minimize the total surface area, we want to find the smallest acute scalene triangle. Here's a test of whether a triangle is acute. We'll start by fixing one side length. We'll call that C. This will be our right triangle, this will be an obtuse one, and this will be an acute triangle with one side length of length C. A right triangle will look like this, and we know that a squared plus b squared is equal to c squared. We'll call this point here with the right angle P. To turn this into an obtuse triangle, we need to move P closer to this third side length C. In doing so, we now have that the sum of the squares of these distances is less than C. To create an acute triangle, we can take this point P and pull it further away from this opposite side. Now we have a squared plus b squared is greater than c squared. This is what we need for an acute triangle. Since it's also scalene, without loss of generality, let's just say our 3 side lengths are a, b, and c in increasing order. And since our 3 side lengths are integers, we must have b is greater than or equal to a plus 1. C must be greater than or equal to b plus 1, which is a plus 2. So we'll plug this in for C and B. We'll FOIL these out and combine like terms. We'll gather all the terms on one side, and this is easy to factor. Both of these factors need to be either positive or negative. Since these are side lengths, it makes sense to make them both positive. We'll get that when a minus 3 is greater than 0, and a is strictly greater than 3. So we'll choose our smallest possible side length, 4, and then we'll pick a couple of small side lengths for the other 2 sides, 5 and 6. Testing that they're acute, the sum of the squares of the 2 smallest sides is 41, which is greater than 6 squared. Now we'll use Heron's formula to find the area of each of our 4 congruent triangles. The semiperimeter is 15 over 2, and we'll subtract these other side lengths. We'll find the square of the area of one of our faces and take the square root, and the total surface area is going to be the area of 4 of these triangles. 15 root 7 is option D. If you'd like me to solve any other math contest problems, please leave them in the comments.